Hey everybody, this is Peter from peterstestprep.com. Today you are going to learn everything you need to know about vectors for the ACT exam. And you're going to learn it really well here because you're going to print out the worksheet. And the link to this thing, you can find it in the description at the bottom of the video. And you follow along the video. Have this worksheet with you. When I tell you to pause and do the problems as we come across them. That's the best way to learn this material, so that you will be an expert on vectors when you come to the ACT. Alrighty, when you're ready, let's begin. All right, we've got the worksheet here, the handout, and I'm going to zoom in and we're going to start where we ought to start, in the beginning. Section 1, what is a vector? A vector is a line segment with a magnitude, that is to say a fixed length and a direction. What does that mean? Well, I'm going to draw a vector. It has a beginning point and an ending point. It has a fixed length. It's always going to be, this particular vector always has that length and it always goes in that exact direction. It's not fixed in space, which means that I can draw the exact same vector in different parts of the graph and they're all exactly the same. Let's go to section 2 and let's learn about vector notation. I'm going to draw a vector here. And what I want you to notice about the vector is that the beginning point is going to be at 1, 0. I'm going to have the end point of it at 5, 5. Now, the way you describe or define a vector is you can assume this is like a right triangle. And it has a horizontal component that has a length of 4. And it has a vertical component that has a length of 5. So this vector, which we can call vector W if we wish, vector W, there's two ways that we can describe this vector. One is I can use pointy parentheses or brackets, and I can write it like that, 4, 5. The little pointy brackets tell us that this is a vector, and in a problem, they'll of course tell you you have a vector. Now, here's where it gets a little bit more complicated or interesting. Usually the horizontal and the vertical components are given their own letter. And usually we'll have the letter I to represent the horizontal component and the letter J to represent the vertical component. So this vector can also be notated 4I plus 5J. And the I and the J would be in bold-faced letters to tell you it's a vector. But again, in an ACT problem, they'll always tell you that it is a vector. As another example, I'm going to draw 4I minus 5J. And again, I can start from wherever I want to. I'm going to start from there. I go across 1, 2, 3, 4. That's the horizontal component, the 4I. And now minus 5J means I'm going to head in a downwards direction like that, 5 units. And that would be 4I minus. All right, let's move on to section 3 and let's let you draw some vectors. How fun. Now, by convention, we usually draw an initial vector starting from the origin. So let's look at this problem here, 3A. On the coordinate plane below, draw and label the following vectors. So first is vector W. I'm going to do that first. Negative 3, 5, and I'm going to start from the origin. So I count negative 3 and then up 5. And I do that, and I'm just going to label it with a W. All right, why don't you guys go ahead then, pause the video now, and why don't you do 2, 3, and 4, draw each of those vectors in and label them, and start all of them from the origin, 0, 0. Vector X is I plus 6J, so it's 1I, imagine it has an imaginary 1 in front of it there. And so 1 and then up 6, and this is a good representation of vector X. Vector Y is negative 2, negative 6, back 2, down 6, like so. There's vector Y, and then Z is 4I minus 2J, so that's 4 across on the horizontal component, down 2 on the negative component, and that will be vector Z. And your drawing should look something like that. Having finished page 1, let's go to page 2, and we're going to go to the top. We're going to learn how to add vectors. Vectors get added tail to head. Imagine you're being given a series of toy train cars and you just attach them one after the other to the other, but you're adding them in the front. What do I mean by that? Well, I've got my two vectors shown here, A and B. So I'm going to add A plus B. There's A. I start from the origin. I then attach B to the head of A, like so. So each vector is added to the front or the head of the previous one. You're moving forward always, not backwards. Now, the interesting thing here is that when you add vectors, you actually get a vector as an answer, which we call a resultant vector. And the resultant vector is drawn as follows. You start where you began your vector series, or your vector train, as it were, and you draw it to the head of the entire train, like so. And that's resultant vector C. And so you would write this as A plus B, right? So A and then B added to that, right? B is added onto A, and that equals vector C. Why don't you move down then on the page, and let's have you try 4B and 4C. 4C is multiple choice. Go ahead and pause the video and do those questions. Taking a look at 4B, we're going to do D plus E plus F. So we start at the origin. There's D right along the y-axis. And then we're going to label that. Let's add E to that, like so. And then F takes us up part back way. And then the resultant vector G will start there and go like that. And there's G. In 4C, the graph below shows which of the following vector sums. Well, you can see that we're adding Z and Y together, Z plus Y. And that gives us X, and so answer B works. And the order doesn't matter. Y plus Z, Z plus Y, it's going to take us to the same place. You're looking for Z plus Y here, but Y plus Z is the same thing. Here's why. If I do Y first like so, and then add Z, it takes me right back to where we finished up before at the end of the vector X, like so. Having now learned to add vectors, let's learn to subtract them. To subtract a vector, well, it's the same as adding the vector, but you draw it to go in the opposite direction. So let's do two examples. Let's do A plus B here. So there's A and there's B. Okay. Now let's do A minus B. A goes up like so. Now B, if I'm adding it, it's going to go to the right a little bit. But I'm subtracting it, so I'm going to draw it in, but it's going to go in the opposite direction. The same magnitude, the same length, but it goes in the opposite direction. And we just label it like so. Let's have you try that. Why don't you pause the video and take a look and try to do 5A. We're going to subtract W minus X minus V, and the vectors there are given. So we're going to start at the origin as always, and there's vector W. Now X is supposed to go to the left, but I'm subtracting it, so it means it's going to go in the opposite direction to the right. V should go down. Well, that would happen if we're adding it, but since we're subtracting V, we're going to have it go up instead. It's going to go in the opposite direction. And so we label them like so. And the instructions did not ask you to draw in a resultant vector, but we could draw that in if we wanted to. I'll make it dotted here, and that would be resultant Z if we wanted it to be so. Let's move on to page 3. Now, section 6 is called finding resultant vectors. We've learned how to draw resultant vectors. Now let's learn how to calculate them. Put all the pieces together that we've been doing here. This should make sense here. So let's take a look at the instruction. It says resultant vectors can be found by combining, adding, or subtracting the vectors. Well, we kind of know that already about, like I said, how to draw them. Let's do the calculation of the same thing. So 6A, we're going to combine vectors A plus B. We're given vector A is 1, 4. So I draw it in like so. And vector B is minus 5, minus 1. So 1, 2, 3, 4, 5, and down 1. So it looks like that. And we'll just call that b, or minus b if you wish. We can do that. All right, we combine the vectors a plus b. Now, let's draw in the resultant, call it c. And let's just count the boxes here, and let's get an idea of what our vector c's notation would be. Well, we're going to count backwards 1, 2, 3, 4 horizontally, and then up 3. So vector c is negative 4, 3. Well, let's take a look and see what happens since we're adding a plus b. Look at the original bracketed notation for vector a and b, 1, comma 4, negative 5, negative 1. If you just add up the horizontal and vertical components here, you get negative 4 and 3. So if you're asked to add or subtract vectors and to get the result of combining them, and they give you the notation, they give you the actual horizontal and vertical components like so, you don't have to draw it out, just combine the numbers. All right, let's have you do the same thing with 6b. We're going to add a plus b, so 5, negative 2, looks like so. And then b is negative 1, 4. So that takes us actually up to there. And my resultant vector is c. And if I just add these two, the vectors in the vector notation, I get 4, comma 2. And if we count out the boxes, the horizontal and vertical components of vector c in the drawing, indeed we get the same thing as we expected, starting from the tail of it, 1, 2, 3, 4, and then up 2. Number 7, magnitude and vectors in the real world. We're going to imagine a boat crossing a river traveling west to east. So here's the shores of the river. We'll put a tree there and put a person there. And the boat is traveling at 20 kilometers per hour west to east. So here's what the boat wants to do, kilometers per hour west to east. Now, the river is flowing downstream at 5 kilometers per hour. Well, that means then if you think about the travels of the boat, if it's trying to go across the river from west to east, but the river's flowing downstream, it's also going to be carried downstream as it's moving across. In other words, it's going to be moving both horizontally and vertically, or another way to say that is in a diagonal line. And it would be expected then to end up down there. And so this would represent here, the resultant vector, if you will, represents the actual distance and speed and the path taken by our boat. Let's introduce a new term, magnitude. The magnitude of a vector is its length, how long it is. Now, happily, when we're talking about vectors, we're usually going to incorporate a Pythagorean theorem situation, or at a minimum, a right triangle situation. So usually like this, we can use the Pythagorean theorem to find the magnitude of a vector. So if we want to figure out what is the actual speed of our boat as it travels this way, remember it's moving both horizontally and vertically at the same time, what we do is use the Pythagorean theorem. So if we just want to call that side C, we can do Pythagorean theorem like so. And we'll get c squared equals 425. And our vector c will have a magnitude. So magnitude has a special notation. You actually were going to put a couple of bars around it. They look like absolute value symbols, so you could use 2 bars as well. That would be your represent your magnitude. Again, this is a multiple choice test, so you don't have to worry terribly much about your notation in your own work, as long as you know what you're doing. And the square root here will be about 20.61. So it's actually moving at a speed of 20.6 kilometers per hour. Okay. Hopefully that makes sense to you. Let's have you try 7A, 7B, and 7C on your own. Go ahead and pause the video. And once you've done them, come back, join us. Seven A, the magnitude of vector W, I can write it like that. It's going to be the square root of 6 squared plus 8 squared. Again, it's just the Pythagorean theorem, and we'll get a magnitude of 10. Now, in 7b, we're using that other notation, minus 5i plus 12j. Well, remember, this is the same thing as the vector negative 5 comma 12, like so. So if we want to use the Pythagorean notation, I can do c squared equals negative 5 squared plus 12 squared. Just use regular parentheses there. And when you work all of this out, we'll get c equals 13. And again, it's a magnitude, so we might want to put absolute value symbols or magnitude symbols about that. Finally, in number 7c, it's kind of like our boat situation. We have a plane traveling north at 600 kilometers per hour. The wind is blowing west at 200. So the plane is actually going to be drifting westward, even as it's flying 600 miles in the northerly direction. These are all right angles, by the way, in case you hadn't figured that out. So a quick Pythagorean theorem here, and we'll get c squared equals 200 squared plus 600 squared, and I'm just going to jump here to the answer. The magnitude of our vector c is 632 kilometers per hour. Well, we're almost done. We go to page 4 for a couple of other ideas here that we want to talk about here. These are not going to come up necessarily very often at all, but it's good to know that, again, they're just kind of easy things to tag on here. In the world of vectors, compass directions, well, you've seen that we've been using compass directions, north, east, west, south. But there's a particular and peculiar language that is used. If you're traveling northeast, we say you're traveling east of north. That means if you're traveling northwest, you're traveling west of north. If you're traveling southeast, you're traveling east of south. And if you're traveling southwest, you're traveling west of south. What does east of north look like? That way. What does west of north look like? That way. East of south is that way. West of south is that way. Take a look at 8A and pause the video, give it a try, and come back when you're done. A train is traveling along a compass direction of minus 50i plus 8j, where I and j represent 1 mile per hour each in the east and north directions, respectively. Draw a sketch of the train's movement below. Now, hopefully you didn't draw it to the right, because even though the I represents 1 mile per hour to the east, in the actual vector representing the train's direction, it says minus 50i. So really the horizontal component is minus 50i. And then there's a northern component of 8j, and therefore the train itself will be heading along like this here. Again, I can just call it vector c if I want, but this guy here, vector c, represents my train's movement. What direction is the train moving? Well, honestly, you don't need to make a drawing. You can tell just from looking here that you're going to the left and up, so we're heading west of north. Finally, we'll go to number 9, scalars. Really easy idea here. A vector can be multiplied by a number that sits next to it and outside of it, and that number is called a scalar. Number 9a, find the vector equivalent to the following expression. So we have 3 times this vector. Well, it's exactly what you expect it to be. The 3 just distributes, and we have so. A quick look at what the consequences are. Here's my original vector 2 minus 4. If I multiply that by 3, this actually should make sense that we're going to make it 3 times longer. It could become 6 negative 12, and it's going to be something like that. Keep this packet as you do with all of the packets that you see on our productions, and put them in a notebook, put them in a binder, and study these. Know all of these if you want to maximize your score in the math section on the ACT. Thank you for watching.